Start with something pretty here first. Just for fun. Alright, you guys will get to play with this a little bit later if you guys want to and stuff, but we'll talk about this later. So, this lesson is going to be on symmetry. This section is actually going to go really fast. When I was first thinking about symmetry and when we were doing transformations, I thought this was going to be a very complicated section. The more I read through the section, this is actually going to be pretty straightforward. The actual math, per se, in terms of calculation you're going to have to do here is going to be pretty limited. Most of what you're going to do in this particular section is going to be very observational. So you're going to have to go back and use your reasoning and rational thinking skills to get through most of this particular section. So this section covers symmetry. Symmetry, let's define that first. If you guys have not already defined symmetry, as I asked you to on the note sheet, go ahead and do that. Go ahead and pause the video and write down a definition for symmetry, and then come back and we'll talk about that. So our formal definition of symmetry is going to be the following: a figure or an object has symmetry if a rigid motion maps the object onto itself. Okay, which is another way of saying that is, well, first we have to identify our rigid motions. Or we have three rigid motions. Okay, we have we have reflections, we have translations, and we have rotations. Translations do not yield a reflection, so we're going to ignore that one. I'll let you guys think about why that's the case. Reflections and rotations all result in symmetry, so those are the ones we're going to concentrate on. So that gives us our two types of symmetry. We have reflectional symmetry is how the book defines it. I know it's reflexive, but reflectional symmetry. And then our other type of symmetry is rotational symmetry. We'll come back and define each of those here in a second. I want to do some examples here, or do kind of little hands-on examples so you guys can see what this looks like. Grab stuff here. I seem to have lost my recording device. Where did it go? There it is. Okay. Alright, so let me turn on my camera here. Cool. So here is a sheet of paper. So I've already marked this up here so you guys can see what's going on here. So this is like folding along the x-axis, is like folding along the y-axis here. If I fold along the y-axis here, you'll notice that I end up with a perfect match. It fits right over the top of itself. That gives this, we fold it horizontally here, so this gives this object symmetry across the y-axis, which is what we call horizontal symmetry. Okay. I don't think the book uses horizontal and vertical, but you are going to hear me say that in terms of vocabulary, so I want to make sure you guys can define that when you see it. Basically folding left to right, or right to left. Let's try it again. Folding left to right, or folding right to left, will give you a horizontal fold, and thus horizontal symmetry. Our other type here, we also have a line running across the x. If I fold along the x-axis, like so, you'll notice here I have perfect fit. It maps right over the top of itself. Okay, so going up down or down up, that gives us a vertical symmetry. So this has reflexive or reflectional symmetry across both the x and the y-axis. So this has reflectional symmetry. We have one other line I did here. I drew this line here along the diagonal connecting this point to this point. So if I fold along that diagonal with this rectangle, okay, you'll notice that this does not fit perfectly over the top of itself. Okay, so if I open this back up here and we look at this triangle, the two triangles do look the same, but when I fold across here, the objects don't lay on top of themselves. So this does not have reflexive symmetry across the diagonals. Now that's not generally true with rectangles. It's true with this rectangle. Squares are technically rectangles. If you did this same example with a square, you would see that squares do work across the diagonal. So squares have both horizontal and vertical. They have horizontal and they have vertical symmetry, and they would also have the diagonal symmetry. So these 2 points would lay right on top of each other. Okay, so squares has some slightly specialized properties over rectangles in general. Okay. So that's reflectional symmetry. Our second type of symmetry is rotational symmetry. So rotational symmetry it's symmetry where we can rotate an object less than 360 degrees and at some point we get the same object we started with. So, for example, here with my rectangle, if I rotate it 90 degrees, that's not the same object that I started with. If I rotate it another 90 degrees, so now I'm at 180 degrees, I have the same rectangle I started with. Okay, so that's an example of rotational symmetry. Let me give you another one here. This is an example of something that doesn't have rotational symmetry. This is my paper stapler. Some of you might remember this thing from the classroom. Alright, so at 0 degrees, I rotate it 90 degrees. No rotational symmetry. I rotated it another, so we're at 180 degrees now. It's not what we started with. 270 degrees, no rotational symmetry. 360 degrees, we're back. We have the same object that we start with. So it has rotational symmetry at 360 degrees, but that violates the definition because every object you can think of has rotational symmetry at 360 degrees. You have rotational symmetry at 360 degrees. That's why when we look at rotational symmetry, we define it specifically to be rotations of less than 360 degrees in order for that symmetry to exist. Okay, so this particular object has no rotational symmetry. Okay. All right, let's go back to the rectangle here just for a second. So we have a special type of rotational symmetry. This is the special case that you'll see on the notes there. So you'll notice that we didn't have rotational symmetry at 90 degrees, but we did have rotational symmetry at 180 degrees. So we have something called point symmetry. So point symmetry is when we have symmetry or rotational symmetry specifically at 180 degrees. So if I can rotate an object 180 degrees about a point, I have specifically rotational symmetry. I'm sorry, specifically have point symmetry. So that's your special case of symmetry here. It's all still rotational symmetry. It's just a special name that we have here. You will see that come up in the homework assignment. Let's see, what else do I have here? I think that covers it. If you need some specific examples, I can make some up in class. I want to go back to weave silk. I want to do a couple of fancy examples with weave silk that you guys can take a look at so that you can have something to play around with. If you go to weave silk, that's weavesilk.com. If you go to weavesilk.com, you guys can play around with the same app that I'm messing around with here, and you guys can create your own objects and do all sorts of crazy stuff that way. So let me turn this off and we'll go back to weave silk. Alright, so if I go back to weave silk, so let's talk about some of the things here. Everything I'm going to do here, I'm going to do in fourfold rotational symmetry. So that's the middle point on the slider here. So fourfold rotational symmetry. And right now I have mirroring across the center turned off. So I'm going to do this in green. If I just make a little object here real quick. Alright, so this object here, let's see what kind of symmetries we have here. I cannot fold this thing vertically, so I can't fold it along the x-axis. This point here does not match up with this point down here. So this does not have vertical symmetry. So likewise, if I go horizontally, this does not have horizontal symmetry. Okay, so there's no reflectional symmetry with this particular shape that I've done here. But it does have rotational symmetry. This point here matches up with this point way down here if I'm rotating the object. Okay, so if I'm folding it, it doesn't work. But if I rotate the object 90 degrees, it matches up. So it's going to have rotational symmetry at 90 degrees. I can rotate it again, and I'll have rotational symmetry at 180 degrees. So this has rotational symmetry, and specifically, it has point symmetry. All right, let's do another example here. This time I'm going to turn mirroring across the center on. So I'm going to turn this on, and we'll make a little object here. We'll see what we end up with. So we have some sort of crazy square looking thing this time. So I can fold right across the middle here, horizontally, and then fold vertically. And that'll give me, that gives me vertical symmetry. I can do the same thing folding across the y-axis, bring this point across here, and I will have vertical symmetry. I'm sorry, horizontal symmetry that time. I also have symmetry along the diagonals. You'll notice here, so kind of like a square, I can draw lines through the diagonals here, and I can fold this thing on top of itself. Now that's a byproduct of the fact that I used fourfold rotational symmetry. If you change this to twofold rotational symmetry, you won't have that same effect. But with fourfold rotational symmetry, it does work out that way, where the diagonals will fold over the top, will maintain symmetry. So this has got all sorts of reflectional symmetry on it. Let's see about rotations. It has rotational symmetry all over the place. So this point here, 90-degree rotation brings me to this point. And then 180-degree rotation brings me to this point. So this has point symmetry, so it has rotational symmetry. So yeah, this particular object has a little bit of everything. Let's go to 2-point rotational symmetry, and we'll try this with mirroring across the center. We'll see what we end up with. So if I just make something really quick here, I don't like that one. Let's try another one. There, let's use that. That's good. Okay, so this is going to have reflectional symmetry across the y-axis, so I can fold it horizontally, and this will lay right on top of itself. Likewise, it's got symmetry along the x-axis, so it's going to have vertical symmetry. It does not have symmetry along the diagonals. It does have rotational symmetry, but the rotational symmetry doesn't happen until we get all the way over here to 180 degrees. So think about it, if you literally rotated the computer screen, if you rotated it 90 degrees, you wouldn't be at the same spot that you started at right now. If I rotated 180 degrees, though, I do have symmetry, and it would be right over the top of itself. So this does have point symmetry. Okay, you guys can play around with this and see what you guys can come up with. Just make funny little objects and stuff, and see what kind of symmetries you guys can observe. All right, that'll bring this lesson to an end. We will, if you have any questions, bring them up during class, and you guys will have time to work on this. Work on the book assignment during class. The book assignment is largely, it's going to be, they give you shapes and objects and flags and all sorts of stuff, and they ask you guys to identify how many types of reflectional symmetry it has, or to draw pictures and to identify the specific types of rotational or reflectional symmetry. So we'll go through all that in class. If there's any specific calculations that we need, you might need to know how to find the angles of vertices of larger objects like pentagons and hexagons. If that turns out to be the case, I will cover that with you guys in class. All right. I'll see you guys in class. If you have questions, please let me know.